Hi, it's time for another math easy solution. Today we're going to discuss applications of integrals and now look at arc length and basically go over the definition or proof of this. Well, first of all, we have to ask ourselves, well, what do we mean by the length of an arc? Well, one way of thinking about it is we might think of fitting a piece of string to the curve in the figure below. Let's just draw this figure like this. So this is the curve that we want to measure. How long is this arc length or this curve? And basically the idea is, we could think about it as, basically let's say fit this curve with a string. Let's put it in red. Let's say we're fitting it across, and basically now this is the string. And then if we were to flatten out that string, it would be about, let's say, this long. So this is the same string above. And then we get a ruler and basically measure it. And this is basically our arc length, or length of curve. Or length of curve. So that's one way of pretty much thinking about what we mean by length of a curve. So that's one way you can measure it, get a string, etc. But obviously you can't just put a string on any type of curve. Basically, this method is too difficult to do with much accuracy if we have a complicated curve. So instead, we need a precise definition of the length of an arc of a curve. In this same way we developed for basically the other applications of integrals in terms of area and volume, as shown in my earlier videos. So make sure to watch those, and I put some links in the video links below as well. So if the curve is a polygon, we could easily find its length. If it's a polygon such as, let's say, an octagon like that, etc. Actually, that's not an octagon, that's a pentagon, but it's really bad shape. You could easily just find out each of these lengths. It's pretty obvious. You just go break it up and solve for it. So we can just add up those length of segments that form the polygon. So since we can easily find its length, one way of defining for a general curve, which we'll do here, is basically thus to define the length of a general curve, we will first approximate it by a polygon, and then by taking a limit as the number of segments of the polygon increase and go to infinity. And this is the same process for the case of a circle, where the circumference is the limit of lengths of inscribed polygons, which I'll draw in a bit as shown below. Also, you see my earlier video and the video link below on the proof of pi, and show how it's equal to 3.14, etc. Which I use in this same method to prove here. And I'm doing this video at the exact same time as, well, March 14th, which equals to Pi Day. So it's 3.14, etc. So that's the month 3, etc. So anyways, make sure to watch that video, especially on Pi Day. Hopefully I can upload it before tomorrow, but otherwise ignore that. But anyways, watch the video. So now if we look at the circle, I'll just show you what I mean. If you were to inscribe polygons in it, let's just draw a square initially. And then so if we inscribe a square, and then you could easily measure the lengths across like this, and then just add these all up. And then as we increase the number of inscribed polygons, increase the number of segments of the polygon. So in this case, we'll do something like this, which has 1, 2, 3, 4, 5, 6, like 7. This is an octagon, so we go to a square to an octagon. As you can see, we're getting a better and better length across, and we keep doing it, something like this. I'm just going to draw a bunch of sides. It's not too well drawn, but anyways, you get the idea. You just draw a bunch, get smaller and smaller until you get even closer and closer to the exact circle. So as you go to infinity, you're going to obviously get pretty much the exact or getting close and closer to the exact circumference of the circle. And ignore my bad drawings, but you understand the point. So now let's just suppose that a curve is defined by the equation y equals f of x. So again, we're looking at a general curve, not a circle or a polygon, etc., where the function f is continuous on the interval a is less than equal to x and less than equal to b. So if we were to graph a general curve that is continuous, this is x, this is y, so let's draw it something like this. So we have something like this where it's from a to b. A, b, this is our curve c, where this equals to y equals f of x. And now for this curve, we can obtain a polygon approximation to this curve C by dividing the interval a to b into n sub-intervals of equal width delta x, and endpoints x0, x1, all the way to xn, etc. So let's give some more space here. So basically, if we were to break this up, we would get something like this, where let's say we break it up into n intervals, and we keep going across like this. Yeah, so we have something that looks like this, where this a value, that's equal to, well, x0, and then this is x1, and then etc. It just keeps going on and on. This is our final one, xn. So b equals xn, and then at this point right here is xn minus 1, etc. So we go 1, 2, 3, 4, 5, and here let's just pick, yeah, here I'm just going to pick a value, random one here. This is xi, and at this point is xi minus 1. So as you can see, is you're just subtracting 1 from each one. So 1 before it's x0, and you keep adding 1. So xi minus 1 right here. Yeah, so now if yi is just simply f of xi, so as in this case we had here would be, yeah, I'll draw it right here, so yi equals 2 f of xi. So we'll just plug it in, f of xi. Then basically the point pi of basically xi, yi lies on the curve C, and the polygon basically lies on the curve, this whole curve, and the polygon with vertices p0, p1, p2, etc. all the way to pn, and that polygon is an approximation to C. So what this means basically is that each point here, this one we'll call it P0, at this point is P1, and again, and then at this point here, so we keep going on and on at every single point, where at this generic point right here, Pi, again, it's a function, or the point is at the xi and yi values right there. So we have this, and then if you connect the lines, you have a polygon, or at least the lengths of the polygon right here. So this polygon is an approximation to this curve. So now we could basically sum up every single one of these lengths, and then we eventually get an approximation for the curve. So yeah, basically as I just showed, the length L of C, or yeah, we'll call it L, so the length of the curve C is approximately the length of this polygon, and the approximation gets better as we increase basically n, as we increase the number of n. If we had infinite n's, it gets closer and closer to the approximation. And we can illustrate this by zooming in on the arc of the curve between the points pi minus 1 and pi. Basically, if we look at this section right here, or just this curve over, I'll just erase, because we're not dealing with the area, we're just dealing with this right here. So from pi to pi minus 1. Now let's write that here. This is pi minus 1. So if we just zoom in on that, we have something like this. So the first segment is just, it's already just one interval right here. I mean, if the delta x was what we have it, and then as we basically here, so from points pi minus 1 to pi, and show how the approximation becomes better with smaller values of n, or n getting larger. It's the same idea. N gets larger, and delta x gets smaller. So as you can see here, this approximation is pretty off, but then as you get into, let's say, a half, which is about roughly here, we get a slightly closer. Let's get 2 points, get something like this, like that, and then as a third point, yeah, these points are a bit off, they're not to scale, or I'm getting them off, but as you can see, the more points you get, basically the closer and closer your approximation gets. And you could just go here, better approximation. So that's pretty much the idea. Yeah, thus basically we can define the length L of the curve C as the limit of lengths of these inscribed polygons, if the limit exists. Obviously, if it goes to infinity, etc., well, you can't solve that. So limit or I mean length equals limit as n approaches infinity. So we can define it like this, as the summation as I goes to 1 all the way up to n subintervals of the length pi minus 1 up to pi. And this sign right here pretty much means the notation pi minus 1 to pi, this absolute value signs around there. This just simply means a distance from point pi minus 1 to pi. And again, it's looking for the absolute value of that distance. Yeah, so again, basically as you increase the number of subintervals, how much you break the curve into parts, the closer that the accuracy gets of the approximation. And also notice how the procedure for defining arc length is very similar to the procedure we use for defining area and volume in my earlier videos on applications of integrals. Make sure to watch those in the video link below. Basically, in step 1, we divided the curve into a large number of small parts, which we just did. Then we found approximate length of the small parts and added them. And finally, we took the limit as n goes to infinity. Yeah, and basically that's our approximation. But the problem with this definition of arc length, which we just showed, is not very convenient for computational purposes, because it's pretty much saying find distance manually, etc. But we can derive an integral formula for the length L in the case where f has a continuous derivative. So if the function is continuous and has a continuous derivative, and again, such a function f is called smooth because a small change in x produces a small change in f prime of x. So basically we're saying that the limit does not go to infinity, etc., or so that it exists. Yeah, so basically to derive this, let's basically if we let basically delta yi equals 2 yi minus yi minus 1, then what we have, well, first let's draw this out. Let's look at that same segment. So if this is our pi, this is our pi minus 1. So at this point right here, that's just yi, and here this is at yi minus 1. So that's the value there. And also we have distance the x value xi minus 1. And all the way down here we have, this is pretty much xi. So that's just at xi. Then we have yi, and then yi minus 1, xi minus 1 here. And basically this length across, this length across right here, this equals 2. If I were to draw this out like this is pretty much delta x, and that equals 2 xi minus xi minus 1. And again, this is delta x, and pretty much right here, delta xi equals 2 delta x for all values, because we've defined it as equal subintervals for all values of I. So they're all the same, all the widths are the same as we defined. And likewise for the y values, for the difference we have it like this. So this difference is basically, let's do this arrows. Yeah, this difference is just delta I, and again that just equals to yi minus 1. And now the distance of this that polygon that we're gonna have, or that line segment, is basically gonna be from this point to here, and this length is pretty much pi minus 1 to pi. So this is that segment we have for, or the length of that segment that we had from xi minus 1 to xi. So that's the length right here, and as you can see, this is just a right angle. We could just apply basic Pythagoras. So we could recall Pythagoras Theorem, Pythagoras right here, and recall that we have, if you have a triangle with a right angle, then this is A, if this length is B, this is C, then pretty much C squared equals to A squared plus B squared. So what that means in our case, we have this, we could apply Pythagoras theorem, and we get, let's write thus, the length pi minus 1 to pi is basically equal to the square root of now our a and b. A is delta x and b is delta yi. So we have this xi minus 1 squared plus yi minus 1 squared, which right here just equals 2 delta x squared plus delta yi squared. Let's do that. And now the next step in this proof is, well, to recall the mean value theorem, because basically I want to write this as a derivative, and you will see why I want to do that. First, basically, if you recall the mean value theorem, if the function f is continuous on the closed interval from a to b, closed, this means it exists. This includes the interval at a and b. And if f is differentiable on the open interval a and b, then there exists a number such that the derivative is the average slope of f between a and b. So make sure to watch that video in my earlier videos in the link below. Basically, what this means is saying that there exists such a number c such that the derivative at this point is pretty much the average slope. So which equals to fa minus fb, which is again rise over run, b minus a. And if you were to draw this out, just to recap on the mean value theorem, if you have a curve like in our case like this, so basically right here, if we have this random curve, I'll go with this as y equals f of x at b, and this is at a, then the average slope is pretty much this. Just connect the two dots together. That's the average slope. And I'll just keep going on and on. So then there exists a number, and as you can see why it's true, such that this average slopes are the same across like this. So basically this and this same slopes. So then that means that this very point, this is the point C where the slopes are the exact same. So basically f prime of C is equal to, well, pretty much that value. fb minus fa over b minus a. This is better a. Yeah, and thus in our case we define our function and its derivative as continuous on that interval a and b. Thus what we can have is basically thus in our case we can simply let c equals 2, let's write it xi star. So we'll let it equal to that. Thus, because ours matches the criteria for mean value theorem, thus there exists a number such that, this one right here, xi star, such that f of xi star is basically equal to f of xi minus f of xi minus 1 all over xi minus xi minus 1, which just equals to delta yi over delta x. Let's write this a bit better. And if we were to rearrange this, thus we have delta yi, and then move the delta x across. So delta yi equals 2 f prime of x star, fxi star times it by delta x right here. So now we can plug this into our formula. So what we have is the distance pi minus 1 to pi is equal to delta, what's it called, square root of delta x squared plus where we have over here delta yi squared. Now it becomes, when we plug this inside, this equals to delta x squared plus, now f prime of xi star, and then delta x. This is delta x, and then all squared. And now if we simplify it by squaring inside there, we get delta x squared plus, now we have f of Yeah, so it's pretty much tedious to getting this proof down, but as you can see, getting simpler and simpler. And then we have here delta x squared. And now we could factor out the delta x squared and take it out of the square root sign. So what we actually have now is integral 1 plus here. So when we factor it out, this is the star, and then squared, and then times it by, well, square root right here, delta x. So I just factored it out. So we have that square root delta x squared. But we also know that, well, yes, since in this case right here, square root delta x squared is always greater than 0. And also, yeah, because of the delta x is always greater than 0. So we have delta x is also greater than 0 in our case. Can't be 0 because we're not defining it. Yeah, we're not having a 0 value. It's getting closer and closer to 0 when we take the limit, but doesn't actually approach 0. So delta x is always greater than 0, so we don't need to worry about the signs if it's plus or minus. So it's always greater than 0. We don't need to worry about doing absolute value. Thus, we have that the length from pi minus 1 to pi is equal to square root 1 plus the derivative f of xi star, and then this one right here, let's put this like this, squared times it by delta x. So that is our length. And basically thus, by the arc length definition, the arc length definition, which we went above, we have now L is equal to limit as n approaches to infinity of the integral from, not integral, from the sum from I equals 1 to n of the distance from pi, or the absolute value of the distance pi to pi minus 1, and this equals 2 when we plug that inside, limit as n approaches infinity of this sum, let's write it a bit neater, sum n, this is from I equals to 1 of up to n of square root 1 plus the derivative here, xi star, this is going to be, let's put the bracket around, squared, and then we have this delta x right there. So we're summing this up n times as n goes to infinity. So this, put it all together, this is our approximation as a limit of infinite sums. And now if you look at this formula right here that we've derived, recall that this expression is the same expression for the definition of a definite integral, and you could see that in my earlier videos on definite integrals. So what this means is basically this length L is simply the integral from a to b of square root 1 plus, and then we have here f of the derivative f of x. Yeah, derivative, I'll put a square bracket to get different from this regular brackets, squared, and then dx. This is the same expression. You can see my video on definite integrals and its proof to how we derived that in the definition. So this is pretty much the definite integral. And in this integral, we don't need to worry about it not existing, because this integral exists simply because, well, the function f and f prime are both defined in our definition as being continuous. Thus, the integrand is also continuous in this. So when you try to find arc length, you have to make sure that the function and its derivative are both defined and continuous across a and b. And again, so what this just means is, and again, this integrand, that's the function inside, i.e. 1 plus f, I'll just do this a bit better, this function, is continuous. So this integrand is continuous, and that means the limit exists. Yeah, I mean the integral exists, and the limit too. So thus, in summary, we have proved the following theorem, basically the arc length formula. If f, the function f and f prime are both continuous on the closed interval a to b, then the length of the curve y equals f of x on the interval a is less than equal to x, less than equal to b, is simply L is equal to the integral from a to b of square root, I'll just put this in here first, 1 plus right here f prime of x squared, and then it's all square rooted, right? I'll try to write it a bit neater. One more try, square root, and then dx right here. So that's the formula we just derived, or in Lebanese notation, which I explained in my earlier video. You can see the video link below. Notation right here. What we have is L is equal to, you could also write it as integral from a to b, wait, it's better, L, of square root 1 plus dy over dx, this squared right here. So that's the same thing, derivative dx right here. So we're writing the derivative in Lebanese notation. Let's erase this. Why isn't it erasing? Okay, finally it erased dx. So you could write it in either way, and I'll show in my later videos. This one's pretty useful as well. I'll just circle. This is the more common one used. Anyways, that is all for today. If you learned from this pretty extensive proof video on arc length or length of a curve, it's pretty interesting. And again, you could always download these exact notes on the link below. And thanks for watching, and stay tuned for another math easy solution.